Actually, today it is lecture number 39. We will talk about finding eigenvector. In last class, we had already discussed about finding how eigenvalue, and also a few more things we will discuss in detail regarding eigenvalue as well. And after that, once we cover everything regarding finding process of eigenvalue, then we will go to discuss about finding eigenvector. And I had already told that in the definition of eigenvalue and eigenvector, first we are defining eigenvector. In the process of defining eigenvector, we encounter eigenvalue as a scalar multiple or a scaling kind of things. Eigenvalue is coming just a scaling factor kind of things. Otherwise, we first need to define eigenvector. But when we go to calculate algebraically eigenvalue and eigenvector, first we need to calculate eigenvector, then eigenvalue, then we are going to calculate eigenvector. That means algorithmically or practical thing. This concept is reverse. That means first we need to find eigenvalue, then we will go to find eigenvector. So further, I will give a recap of finding process of eigenvalue, and there I will discuss something more what we had already discussed in last class. After that, I will go to discuss in detail about how to find eigenvectors. So it is main important part of this module that if you are having enough idea how to find eigenvector, whether it is geometrically or whether it is algebraically. So for geometrical kind of simple linear transformation like reflection, projection kind of things, easily you can visualize eigenvector, and rest of things also you can visualize eigenvalue as well. So there you don't have to do any tedious kind of algebraic calculation. Just after drawing things, you will get to know what is the eigenvector and what is the eigenvalue. But if you go for a higher dimensional kind of a space where if you define linear transformation, then things would be a little bit complicated. But there is no issue. Always there is a technique. Linear algebra, it looks very easy to solve. So because everything looks linear and it is dealing with matrices. So calculation might be a little bit cumbersome, but things are very much perfect that you will get definitely. There is a certain thing to see to talk about eigenvalue and eigenvector. And if time permit, then I will go to discuss about diagonalization. And once we will have idea of diagonalization, then we can talk about a spectral decomposition. That means um, positive definite symmetric matrix can be decomposed into very simple matrices. That kind of, so diagonalization leads to very interesting kind of idea that if you are taking a matrix which is positive definite and symmetric, then easily you can decompose this matrix into three simple matrix: V, lambda, V transpose. So here V is what? V would be orthogonal matrix, orthogonal matrix, OGM. In short I am writing it. And lambda is what? It is a diagonal matrix. So in short I will write it DM, diagonal matrix. That means it is having a non-zero entry along the diagonal, and every off diagonal entry happens to be 0. And V transpose is again an orthogonal matrix. So that simple structure it is taking. Remember that when you can do that, when you come to know that this matrix A is a positive definite and symmetric matrix, then you can write in this decomposition form. So this one is purely based on the process of finding eigenvectors and eigenvalue. So that's where I'm recalling recap of finding eigenvalue and eigenvector. So one uh, for few special cases I am going to talk about how to find eigenvalue. So if you are taking a very simple 2 by 2 matrix and it will have just 4 entries, then what is the characteristic equation or characteristic polynomial? It would be just easily we can write it lambda square minus trace time lambda minus determinant. Sorry, it would be plus here, plus determinant equal to 0. Okay, just equal to 0. If you solve it directly, you will get eigenvector. The process I had already discussed, that how to find eigenvalue. So that means if you are having a matrix, then define a new matrix that we are calling it A minus lambda times identity matrix, and equate the find the determinant of this matrix and equate to 0. In that process you are getting a polynomial in lambda of if suppose A is n by n matrix, then you will get a polynomial in lambda of degree n, and if you solve that polynomial, then the solution of that polynomial will be what eigenvalue of the corresponding matrix. So if you are taking 2 by 2 matrix, then polynomial, this polynomial, especially that characteristic equation is very simple. You can write like this way. If you are having 3 by 3 matrix, that means there is a matrix with 9 entries, then its characteristics polynomial, easily you can write it like this way: negative lambda q plus trace time a lambda square minus c time lambda plus determinant of a. So here C is a little bit cumbersome to calculate. You will come to know from the matrices. So C is definitely it is coming from, it is just function of all these entries, coefficient of matrix or coefficient matrix or this matrix. So C is dependent on that. So just either directly solve this one and you will get characteristic equation, or directly you can write like this way. Here what you do, you don't have to find the determinant of a minus lambda I, and you don't have to find that. Here directly you are able to write. That means you can calculate trace of a. Trace of a is what? It is just sum of diagonal entries of the given matrix. So if you sum it up, then you will get a trace. And what is the determinant? That means you know how to find determinant of a matrix. So it is a very shortcut technique to find characteristic equation of a given matrix. It is a shortcut equation, you can say that. Otherwise uh, regular equation is like this way. Like this way you have to find the determinant of a minus lambda I and equate to 0. So that is the regular process to find eigenvalue of a given matrix. So even if you go for n by n matrix, there is a shortcut technique that it says that you can replace this characteristic equation like this way. Uh, it is very simple in term of trace and uh, determinant of a, and in intermediate coefficient it would be calculated with the help of the given matrices. And you need for few further identity. All these are part of uh, theory of equations, because you haven't go through theory of equations, so I won't discuss. Even here in this course I am not taking very complex kind of matrices. I'm just taking 2 by 2, 3 by 3, 4 by 4 kind of matrices, so they are easy to find eigenvalue of those kind of matrices. I won't go to find eigen value of 100 by 100 matrices or 1000 by 1000. MATLAB and R and other software are very sufficient to give value of those high size matrices. You can use that. So one example further we can say that we say that if lambda naught it is an eigenvalue of a square matrix, and here I'm defining a new term with respect to eigenvalue, that we are calling it algebraic multiplicity of a eigenvalue. So suppose we are having a square matrix A, and lambda naught is one of the eigenvalue of that. So here algebraic multiplicity. Okay. Multiplicity, define it like this way. So some lambda naught is a eigenvalue of a square matrix A, so it will have an algebraic multiplicity k if we say that lambda naught is coming, uh, lambda naught is a root of the characteristic polynomial with multiplicity k. That means when you are writing characteristic polynomial, this of the given matrix A in term of lambda, so you factor into two form. One form, so that means lambda naught is coming as a root of the characteristic polynomial in k times. That means lambda minus lambda naught to the power k factor is coming, is present here in this characteristic polynomial. And here g of lambda is another polynomial where lambda naught is not a root of g of lambda. So that means you can observe that lambda naught is coming k times as a root of the characteristic polynomial. That's where this k we will call it what? Algebraic multiplicity of the eigenvalue lambda naught. So in short, I will write it k dot m dot, algebraic multiplicity of lambda naught, of lambda naught. You can write it. So it is very essential to know algebraic and geometric multiplicity. When I will discuss about eigenvector, and that time I will discuss about geometric multiplicity as well. So here uh, we have to find the characteristic polynomial. Okay, then we will find eigenvalue, then we will find algebraic multiplicity of the following given matrices. So three things we have to find. Well, first we have to find what is the characteristic polynomial. So how we will get characteristic polynomial? By just finding the determinant of a minus lambda I. Just find the determinant of a minus lambda I, that will give your characteristic polynomial. Okay, then once we are having characteristic polynomial, then we can do factorization of the this characteristic polynomial in terms of roots of that polynomial, and from there equating to 0 we will get to know eigenvalue, and we will see that which eigenvalue is repetitive in nature. That means how many times it is coming. So that number of times we will call it algebraic multiplicity of that eigenvalue. So here one example I have taken here. You can see that it is how it is 5 by 5 matrix, 5 cross 5 matrix. So at most how many eigenvalue is possible? So 5 eigenvalue is possible, and it is a odd number here. Size here 5 is odd a number, so you can always guarantee that definitely there is at least one real eigenvalue. But luckily what we observe that it is a upper triangle matrix, so the entries which are along the diagonal element will serve as an eigenvalue. So these are the eigenvalue. So it is having 5 real eigenvalue. First eigenvalue is this one, 1, 2, 2, 1, 1. All these are eigenvalue. So if I am asking find the characteristic polynomial of this one, that means determinant of, if you solve determinant of uh, a minus lambda I and do little bit manipulation, you will come across to see that determinant of this one is nothing. It is a polynomial, uh, 5-degree polynomial. So in short I am directly writing in the linear factor. So it would be what? So it will have root 1 and 2 and root 1. That means you can write this determinant of a minus lambda like in this polynomial, lambda minus 1 square into, sorry, not a square, it 1 is coming 3 times, lambda minus 1 to the power 3 and lambda minus 2 to the power 2. So it is a quantic polynomial characteristic equation of this one. So here you are having two root. One root I always give in lower value, call it like this way. So here you are having two root of this polynomial. If you equal to 0, this one. So one root is equal to 2. Another root is what? 1. So this polynomial is having two root. One is 2. Another root is 1. Lambda 2 is 1. Okay. So how many times 2 is coming? You can observe the copy here exponent. So 2 times. 2 is coming 2 times. So that's why algebraic multiplicity of 2 is what? Eigenvalue 2 is algebraic multiplicity of lambda 1 is 2, and algebraic multiplicity of lambda 2 is what? That one is 3. Algebraic multiplicity of lambda 2, that means eigenvalue 1 is uh, it is coming 3. So you have already observed the algebraic multiplicity as here it is 3. Okay, so just you have to find a characteristic equation. So this is the characteristic equation. So notation, I had given notation, you can call it fa is, a will come as a suffix fa of lambda. Okay, so you can call this is the fa of lambda. Okay, you call it like this way, fa of lambda. That means it is your characteristic polynomial, and 2 is the first eigenvalue and 1 is the second eigenvalue. I had already mentioned that I will always call largest eigenvalue as the first eigenvalue and the least eigenvalue as the last eigenvalue. That's why I'm taking lambda 1 equal to 2 and lambda 2 equal to 1. So it is there is an intention. That's why I'm giving this notation or this kind of special sorting. Okay, I'm taking one more matrix. This matrix A. It is having entry 1 1 1 1 1 1 1 1 1. Okay, every entry is 1 1 1. So definitely, what would be characteristics polynomial of this one? Just find the characteristics polynomial of this one. So consider this one as a homework. What you will do, so you have to find determinant of this matrix A minus lambda times I, and this will give your polynomial in cubic polynomial. So you can call it cubic polynomial. It is guaranteed that negative cube cube of a lambda as a cube will come here, then plus trace, we are calling it, what is the trace? Trace is 3, sum of diagonal element. So it would be 1 plus 1 plus 1, that is 3 times lambda square, then one scalar factor will come. So that also you can design it, there is no issue. There is a technique to find this C. So I am giving right now as a homework. You come to know what is C. And determinant of this one would be what? Definitely this one is a singular matrix. Why? We observe uh, column, dependent column. So you can say that if you call this one is C1 and C2 and this one is C3, then you observe that C1, C2, C3 all are same column. So definitely determinant would be what? 0. So you got a polynomial like this way. So one guaranteed eigenvalue would be what? One eigenvalue would be 0. Other would be non-zero eigenvalue. So it is your task to find other non-zero eigenvalue of this given matrix. So usually sometime having idea of matrices will also give what would be eigenvalue. And there is a relation between eigenvalue and trace. Also there is a relation between eigenvalue and determinant of matrix. So suppose you are having a 3 by 3 matrix, and definitely it will have at most 3 eigenvalues. Suppose we are calling those eigenvalues lambda 1, lambda 2, and lambda 3. And if you multiply these eigenvalue, then product of eigenvalue, it happens to be equal to determinant of the matrix. That's why last equation I had already written. So product of eigenvalue is always equal to value of the determinant of a matrix. One equation. Another equation, it is saying relation is saying that sum of eigenvalue happens to be equal to sum of diagonal element of the matrices, and that means that one is equal to trace of the matrices. So you can say that lambda 1 plus lambda 2 plus lambda 3, it would be equal to what? It would be equal to 1 plus 1 plus 1, sum of diagonal element. That is what we are calling, this one is trace. It is trace of A, the matrix A. So that those are the hidden concept of properties of matrices. So from there also we can you can find a value of eigenvalue directly you can find. So you can go few more relation and just solve, and then you will get a one equation, you will get it, then that means characteristic equation you have to equate it to 0. One equation you are having this one, another equation you are having this one. You know that determinant of this one is equal to 0. So lambda 1 plus lambda 2, lambda into lambda 1 into lambda 2 into lambda 3 equal to 0. Another equation you are having lambda 1 plus lambda 2 plus lambda 3 equal to 3. So you are having 3 unknown and 3 equation. Easily you can find all these value. Okay, so here you can get. So I have given enough idea to find the other lambdas. So one I have already told that lambda equal to 0. You can easily see that lambda equal to 0, it satisfies this equation. So you will come across to see that. Okay, the other lambda also you can find in the similar process. Okay, that means you uh, okay, so it is a homework, try to find it. I'm going to discuss further about eigenvalue. So just to forget about this title, I didn't change. I could not get time to change this one. So if you consider n by n matrices, so definitely it will have at most n real eigenvalue. Okay, even if they are counted with algebraic multiplicity. So at most n real eigenvalue a matrix n by n matrix can have. Further, what we can say that if suppose n is odd, then there is a guarantee that the matrix will have at least one real eigenvalue. There is a guarantee. But if you are having I, n is even, then in that case a may not have any real eigenvalue. So one situation is like this way. If you take this matrix, orthogonal matrix like 1 0, or simply take it 0 1, and don't take it here 0, take it -1, minus rotation matrix. Take a very rotational kind of matrix. So what is eigenvalue of this one? If I'm asking to find eigenvalue of this one, so what you will do? You will write a characteristics equation of this one. So what is the characteristics equation? Or first write characteristics polynomial. What is characteristics polynomial? Lambda square minus trace time lambda. Trace is what? Diagonal entries are 0 0, so trace would be 0. That means lambda factor is not there. Linear factor lambda is not coming as a linear factor, and last term would be determinant of plus determinant of a. So what is the determinant of a? If you find determinant, it would be what? 0 plus 1. So determinant is coming 1. Determinant of this matrix is 1. So characteristics equation of this given matrix, suppose we are calling it a, and characteristics equation is coming like uh, lambda square plus 1. Here what is n? N is an even number. Why? Because it is a 2 by 2 matrix. So with respect to this given matrix, we observe that we are getting a characteristic equation which is having no real root. This one is having no real root. So that means it is having the, in that process we will say that the matrix is having no real eigenvalue. It is having just complex eigenvalue. We are not interested in complex eigenvalue. So there is no real root. So simply it implies that the matrix is having no real eigenvalues. Okay, so that is the criteria if n is even. But if n is odd, definitely there is a guarantee that you will get at least one eigenvalue. So consider, so the same example I had already taken and I described this one. So you can see the equation of this characteristic polynomial lambda square plus 1, and what is happening? It is not intersecting this horizontal axis. So that's why it is having no real root. From graphically also you can observe that it is having no real root. Okay, so another things, one scenario here I consider that we are taking a 3 by 3 matrix, and all possible scenario we will discuss what kind of eigenvalue, what are the possible set of eigenvalue a 3 by 3 general 3 by 3 matrix may have. So that scenario I have written it here. So if you are taking a 3 by 3 matrix, then it will have at most 3 eigenvalue. So first scenario I am talking about, there are 3 distinct eigenvalues. So that means if you are having 3 distinct eigenvalue, lambda 1, lambda 2, and lambda 3, that means every eigenvalue is having algebraic multiplicity of having 1. All are distinct. So that's why characteristic polynomial of this matrix A it has been just factored into like this way: lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda 3. So that is the approach. So in that case, lambda 1, lambda 2, and lambda 3, all three are distinct. That means all three are different from each other. Okay, so this scenario we observe. So in that case, every eigenvalue is having multiplicity 1. Another scenario is that where we can observe uh, 2 eigenvalue. In that case, one eigenvalue have uh, algebraic multiplicity 2, and another eigenvalue will have algebraic multiplicity 1. And one more scenario we can observe that there is only one eigenvalue where uh, that repeat 3 times. So that means it say that that eigenvalue is having algebraic multiplicity 3, and there is one more scenario that there is only one real eigenvalue and other two eigenvalue happens to be complex. So in that case, algebraic multiplicity of the real eigenvalue is 1. So we observe 4 scenarios. So these are the only 4 possible scenario where scenario we can observe for a 3 by 3 matrix. So that those scenario I will discuss in case by case. So suppose we are taking a matrix, this diagonal matrix having entry, these are the entry of diagonal entries are 0 and diagonal entries are 1, 2, 3. So easily we can see that characteristic polynomial of this one would be this this cubic equation. That means lambda minus 1, lambda minus 2, lambda minus 1 into lambda minus 2 into lambda minus 3. I have taken negative sign outside, then you can talk about that. So if you equate to 0, then you will get your eigenvalue. So what are the eigenvalue? Call this one. This one is lambda 1 equal to 3, lambda 2 equal to 2, and lambda 3 equal to 1. So we got three distinct eigenvalue, and we can observe that all are coming uh, having multiplicity 1. All these eigenvalue are having multiplicity 1. So that's where what is the algebraic multiplicity of this one? Algebraic multiplicity of 1 is 1. Algebraic multiplicity of 2 is 1. Algebraic multiplicity of 3 is 1. So all the eigenvalues are having one multiplicity. Every eigenvalue is having one multiplicity. So see this scenario, if you try to observe a plot of characteristic polynomial, so you will observe that this characteristic polynomial is intersecting this horizontal axis or zero axis, you can say that, call it in term of lambda, or this one is plot of characteristic polynomial fa of lambda. Okay, so it is cutting the horizontal axis at 3 points. First point is this one, second point is this one, third point is this one. These are the 1, 2, and 3. These are the root, or you can say the characteristic polynomial. Another scenario where suppose we are taking a matrix which is having diagonal entries 1, 1, 2. So here we observe that 1 is coming 2 times. So that's way algebraic multiplicity of 1 is what? 2, because it is coming 2 times. So lambda minus 1 is coming 2 times. So 1 is an eigenvalue with algebraic multiplicity. So it is coming 2 times. So what is the algebraic multiplicity of 1? Eigenvalue 1 is 2, and algebraic multiplicity of second eigenvalue 2 is 1. And what is the scenario of if you are willing to plot the graph of characteristic polynomial, so it will come like this way. So here you observe this kind of very smooth kind of nature, that means quadratic nature. So it is quadratic scenario you observe at once. So that's why it is coming due to algebraic multiplicity of 1, and you don't observe quadratic scenario at 2. You observe, so that's where 2 is having algebraic multiplicity 1. So from the graphical point also you can visualize algebraic multiplicity of a eigenvalue as well. I'm taking one more scenario. So if you take identity matrix is what? So it is a matrix having all diagonal elements same 1. That means 1, 0, 0, 0. First row is 1, 0, 0. Second row is 0, 1, 0, and third row is 0, 0, 1. So this is your identity matrix. So what you observe? So every diagonal entry is 1. So in that case, you all observe that you are getting 1 as a root of this characteristic polynomial 3 times. So that's why 3 is the algebraic multiplicity of this 1, eigenvalue 1. 3 is the algebraic multiplicity. So how you can observe the plot of this one? So plot of that scenario, it is coming like this way. Cubic pattern you observe cubic pattern in the neighborhood of 1. Why? Because 1 is a root of this characteristic polynomial with algebraic multiplicity is 3. That's why you observe a cubic pattern. Okay. Now fourth case where we observe we are having a matrix like this way, and here characteristic polynomial of this one is lambda minus 1 into lambda square plus 1. So we observe here, if you equate this one equal to 0, then you will get only one real eigenvalue, that one is equal to 1. And if you equate the second factor, quadratic factor, lambda square plus 1 equal to 0, you won't get any real eigenvalue. So that means this matrix is having only one real eigenvalue. And what is the algebraic multiplicity of that one? One, because it is coming only one time. So, and what is the, if you graphically try to visualize this characteristic polynomial, so it would be like this way. You don't observe any cubic pattern in the neighborhood of one. Why? Because algebraic multiplicity of one is 1. So that's why you want to observe cubic pattern here. So here such scenario. So if you want to detail about these roots of polynomial, so my suggestion is go and visit book. There is a very very simple kind of book of high school. In high school you have already seen that one higher algebra kind of book, read a very old kind of book. I forget the name of that author. So very famous in plus 2. You can recall those plus 2 book in order to see all these scenario. Okay, so coming to main part of today's lecture, that I had mentioned that in today's lecture I will discuss about finding eigenvectors, how we can find eigenvector. So eigenvector, I had already discussed that if we are having n by n matrix, then how we define eigenvector. So if eigenvector is a very special kind of vector, if we apply matrix over that vector, then it doesn't change the direction of that matrix. It just do at most a scaling of that factor. That means a times v equal to lambda times v. At most, the matrix can bring change in v is what? What that change is a scaling factor. That means av equal to lambda v. And here remember that v must be a non-zero vector. we we should always take, in order to define eigenvector, we always take a non-zero vector. Okay, so consider an eigenvalue. We had already come across to see that how to find eigenvalue of a given matrix. Suppose lambda 1 is an eigenvalue of a matrix, then how can you find eigenvector? So finding eigenvector is equivalent to finding uh, kernel or null space of A minus lambda I. So this A minus lambda I, kernel of or null space or kernel of A minus lambda I, we are calling it what? It is just giving a associated name with respect to this eigenvalue. We are calling it eigenspace associated with eigenvalue lambda, and we denote it by A lambda, sorry, E lambda, we denote it. And then what does it say, how we define E lambda? E lambda, we are saying that it is actually kernel of the matrix A minus lambda I, or another name also we can say that it is actually eigenspace. So first we will define eigenspace. Then if you take any vector from any non-zero vector from that eigenspace, that vector would be an eigenvector of the given matrix. If you take any non-zero vector from that. So what is the best way to represent eigenvector? Take basis element of that eigenspace, that simply you can call it eigenvector. So that is the approach to find eigenvector. So, and hence, so here I have already further written, and hence an eigenvector associated with eigenvalue lambda is a non-zero vector in the eigenspace, corresponding eigenspace E lambda. So what is E lambda? I have already mentioned that it is kernel of the matrix A minus lambda I. So you are already having enough idea how to find a kernel of a matrix or null space of a matrix. So it is just you, what you do, that means you are finding all the vector which satisfy this homogeneous equation. That means A minus lambda I times v will nullify the vector v. And if you simplify, then what kind of form? If you simplify, what form it is taking? It is taking the form av equal to lambda v, and that it says that v is the eigenvector of A. So both are equivalent. So that means finding eigenvector of a matrix is equivalent to finding null space or kernel space of A minus lambda I. Both are equivalent. So equivalency you can observe here. So that's why I have introduced here eigenspace. Okay. And if you are willing to see the geometry, easily you can see the geometry. One example I have taken here. So consider T is an orthonormal projection operator. Uh, it is defined over a two-dimensional subspace in R3. So V is a two-dimensional subspace. Any two-dimensional subspace in R3, we are calling it a plane. So V is a plane in R3. Then what would be what are the possible eigenvalue? So possible eigenvalue, you don't need to uh, find A directly. You even A is what? It is a projection matrix, and T is a orthogonal projection. So what are the possible eigenvalues? So easily from the geometry you can say that there are two scenarios. If you take any two any vector, and with respect to projection there are two scenarios. So if observe, if you are taking a vector which is from mm, like take like this scenario. So suppose you are taking any element from subspace or plane V. So V is any element from V. So if you are trying to find projection of V with respect to plane V, what would be projection of V? It would be the vector itself. So projection of the this vector from the plane, it would be the vector itself. That means you are saying that what is this one? This one is defined as A times V. Here you can observe that. So A times V equal to V. If you are taking any vector from V, okay, one scenario you observe like this way. So that's way we are saying that saying that any vector in this plane, this is the V, and any vector in this plane is serving as an eigenvector for this orthogonal projection. And what is the corresponding eigenvalue? Eigenvalue is what? It is 1. So first eigenvalue is lambda 1 equal to 1. Okay. Now, second eigenvalue, if you take any vector V perp, I am calling it V perp. V perp is definitely, it is perpendicular. It is coming from where? It is coming from orthogonal complement of V. So if you are willing to find projection of V perp with respect to the given plane V, so what would be projection? Projection of V perp would be what? You can easily observe that V perp, that means you are taking any vector along this line. So if you want to project on the plane, where projection would go? It would go to origin. So projection of V perp with respect to this plane V, it would be what? It would be 0. So this 0, you can say that you can write it 0 as a scalar, 0 times V perp. V perp, or better notation you can take it like this one, W. So if you are taking any W, so you call it W equal to V power. So that means W is an element of orthogonal complement of plane, given plane V. So if you are finding projection of W with respect to plane V, so you are able to write it like this way. It is equal to 0 times W. So you got another eigenvector, that one is W, where W is where? W is in the orthogonal complement of V. And what is the eigenvalue? Eigenvalue, second eigenvalue is actually 0. So you got second eigenvalue. Geometrically you are visualizing. You don't need to know matrix. Otherwise you come across to see one basis and easily you can get that orthogonal projection matrix. Easily you can get that. But here I don't want to go that cumbersome calculation. Directly from the geometry you can calculate eigenvalue and eigenvector. So all these are scenarios. Also, what is the eigenspace? Eigenspace with respect to first eigenvalue, that we denote it lambda 1 equal to 1. So we will denote it either lambda, you can denote it by E lambda 1, or simply you can value of lambda 1 is what? 1. So you can simply also denote it E1. So what is eigenspace of the matrix with respect to eigenvalue lambda equal to 1? It would be just the plane V. Why? Because we observe that every projection of every uh, point on the plane, it would be the point itself with respect to that plane. So that's way E1 would be V, and you can say that it is a V is a plane. So definitely it would have two bases. So bases call it one call it give some name that this is V1. It is a plane, so definitely it will have two direction, v1 and v2. So simple notation for eigenvector, you can say that v1 and v2 are eigenvector. This is element representative, this is eigenvector would be v1 and v2. Otherwise if you take any vector on this plane v, so that v would be what, it is a linear combination of v1 and v2. Why v1 and v2 are basis element of the plane, so you can always represent v as a linear combination of v1 and v2. So that is the concept. Similarly, second eigenvalue is 0. So with respect to that, you can denote it E naught. So the E0, that it is already given in picture. You can see it here like this way. So what is E0? It is orthogonal complement of the plane. That means V per. So you got all the idea. Okay. How to find eigenspace. So we are going to find eigenvector of a given matrix as an example. So here I will go a step wise. So here we are having a matrix, entries are 1, 2, 4, 3. So in first step we have to find eigenvalue of the given matrix. So how to find? Just define the characteristic polynomial. So this is the characteristic polynomial lambda square minus 4 lambda minus 5, and factor it into linear polynomial. So it would be in linear term lambda minus 5 into lambda plus 1. It will give two eigenvalue. First eigenvalue is 5, second eigenvalue is -1. Okay, so in second step what we will do, we will find eigenspace. So with respect to eigenvalue 5, we will get e e5 or e lambda 1. So what is the e lambda 1? It is an eigenspace with respect to lambda 1 equal to 5, and in that process just solve this system of linear equation. You will come across to see that e lambda 1 is nothing, just it is a line with direction 1 2, or simply you can say that with basis 1 2. So this is 1 2 is the basis vector of this eigenspace. Similarly you can get second eigenspace with respect to second eigenvalue -1, and you are getting this is the eigenspace. That means it is a line with the basis 1 -1. Okay, and if you are willing to see the plot of this one, in the last step you have to do plotting, and this is the plotting. You can observe that here uh, this one is e lambda 1 or e5, or this one is e-1 or e lambda 2. And you can easily observe that if you take basis element 1 2, easily it satisfy this equation. It says that if you apply matrix over 1 2, it is not changing the direction, it is just 5 it is just a scaling 5 times in the direction of 1 2 itself. So that's why 1 2 is an eigenvector of the given matrix, this matrix A, with a scaling factor 5. That scaling factor we are calling it eigenvalue. Similarly also we can say that 1 -1, it is a eigenvector of this matrix. Why? Because if you multiply this matrix with this factor, what we observe, it is just coming as a -1 times this vector. That means it is another eigenvector with this scaling factor. So this scaling factor is again, I will say that it is eigenvalue of the matrix -1. So you have seen all the geometry. In next class I will talk about diagonalization and further decomposition technique, that spectral decomposition. And I had already given information regarding